Thanks a lot for coming to the last talk of the day. And actually, the layout is a bit different than I expected because this is mostly more presentation style. There's not too much like hands-on exercise. But you will not be disappointed because there's some Google secrets in the talk. So welcome to the sassy machine learning topic, model explainability and production system. So a little bit more about myself. I have a job for sure. I'm a software engineer at Google Cloud AI. Before that, I work as a data scientist, mostly use machine learning to machine. So it's the field called predictive maintenance that uses machine learning to analyze when a machine is going to fail and how long its life would be. And as many of the audience, I also have an unpaid second job. I have been a Kaggler for 2 years. I'm still unpaid because I haven't get any prize yet. I also do robotics competition, like a supervising team to build a vision-based flight control system. And as you play with this like mission-critical system, you start to want to understand like why the model gives such prediction. Like, can I map back the prediction back to the feature space on how which features like forms a strong signal, or is the signal right, or it is overfit? So that's why I get more interested in this topic, and I start to work on it since I joined Google. So here's an overview of today's presentation. The first half part is more theoretical part. So I want to talk about some concept of feature attribution and how does that link to a model expandability. And I will also talk about a concept in game theory, a cooperative game theory called Shapley Value, and how does that can be used to analyze in your model. So if you haven't heard about Shapley Value before, don't worry, I will talk about it. Actually, it is a method that already integrated into SGVBoost and LightGBM. Maybe some of you already play with it. But for neural network, actually, there's an equivalent version. So maybe it's less well known. But yes, there's also Shapley Value for neural network. So after the theory part, I would use one of the Kaggle dataset, which is the English text normalization, to show you how this tool can be applied to analyze your model. And finally, I want to talk about how you deploy algorithm to a production system. It is an experience, so not a common experience for Kaggler for when you're playing competitions, because usually you just train and run a batch prediction. But this part might be a more important practice in the industry. So I will also talk about that. Now, before going into those mathematical concepts, so let's take one step back to try to define what is expandability. So the left-hand side is actually definition is more qualitatively. It's a paper from Binkin. She's a research scientist in Google. And her definition is like expandability is the ability to explain or present in a human understandable term. So it's more qualitative way to define it. So as a data scientist or more math-heavy people, you might want to come up with a more rigorous definition. So I come up with the right-hand side. Can we use a simpler or human understandable model that to approximate original like complex tree ensembles or neural network, and either locally or globally? And hopefully, this approximation can give you some guarantee. So what's that guarantee? I will talk about later. But I would like to define more like rigorously or more mathematically give us such definition. So that leads to a concept called feature attribution. So let's say you have defined your machine learning model, and it takes like m features jointly to make such a prediction. All right, so this is a function f x1 to xsm. And can you kind of like assign the original prediction to each feature? Let's say like S1 contribute 10 out of 100 of the prediction, and S2 give you actually negative effect of this prediction. So that comes to this idea of feature attribution. So the right-hand side, the phi 0 and phi 1 to phi m is actually the feature attribution score. So phi 0 is the bias term, means like if no feature is presented, what is the baseline prediction. And zi is the kind of a Boolean vector to indicate whether this feature is this or not. So if it's this, it should either contribute to some prediction or maybe 0. All right. Let's take a linear model as an example. Linear model, beautiful model, very simple. Suppose that's your true model. Your true model is like x1 plus 10 times x2 plus x3. So that's a very simple linear model. And now a feature comes in. So you want to predict like what happened. What's the prediction in the x1 equal to 1, x2 equal to 0.1, and x3 equal to 10, right? Since it's linear, it's beautiful. What you do is just multiply the coefficient with the feature value, right? But let's take a look in a slightly different way by manipulating this Boolean vector. And what you do is, let's say, if I want to analyze in the effect of x1, we mask x2 and x3. We assign some baseline or assign 0 to it. And then if I want to analyze the x2, I mask s1 and s3, and then use it to put into your model function, get a prediction. And this gives you a system of equations. Basically, the Z is just an identity matrix. And you take the kind of inverse, then you kind of finding out this phi 1, phi 2, and phi 3. And here there's no bias because there's no bias term in the linear model. All right, so beautiful linear model. Usually have very beautiful theory. Now, what if you have a nonlinear model? Like tree ensembles, neural network, how do I analyze in this feature attribution, right? If you just like masking maybe just one each other, you cannot capture all those cross terms. So what a more common practice you do a random sampling. So in your Z matrix, you randomly sample a Bernoulli distribution, and then you're kind of like getting this matrix and randomly sample it, and then you solve this problem by least square, maybe with some penalty. And then you can solve this phi 1, phi 2, and phi 3. And this actually is a very popular method called LIME. If you search it, so LIME does this random sampling, and then they fit a linear regression. So what's the problem of random sampling? You might get different results at different rounds. So if you want to get an explanation for a model, and every time you get different results, that's quite scary to me. Can we do a better job, right? Can we have a more deterministic algorithm? So because you can also say I can do a random sampling with a deterministic sampling scheme, but that also have problem because for some interaction, for example, you have a very complicated interaction. This sampling might not help you to capture that. So to do a better job, in the recent research, they introduced this concept of Shapley Value that comes from game theory. Before going to mathematics, I want to talk about the background of this Shapley Value. Right. Now, suppose after this talk, you want to either go back home, go to a restaurant, or we go to airport, right? And since Uber is quite expensive in San Francisco, you want to do an Uber pool, right? They pick up maybe A, B, C from this hotel. And at each edge, it is cost driving from one point to the other. So for example, if you start from this hotel to point A, it costs you $6. And same, like from point A to point B, that costs you $7. And now it comes to naturally, it comes to question like, how can we split costs between A, B, and C, right? So the most like naive way, let's do just do a split them evenly. So if we are friends, I don't mind do that. But if we are strangers, like I wouldn't pay $7 like if I'm because going from here to my home is only cost $6. So split them evenly doesn't work. Now, there's also another solution. Like, let's say, what about we split based on the shared distance? So what does that mean? For the first, if A, B, and C form a Uber pool, it would go from first hotel to point A, then to point B, then to point C. And all of them share the same distance from here to point A. So all of them should pay at least $2. And then same for the point A to point B distance, B and C share those, right? So they should pay like half, split that cost, pay half. And this looks like pretty good, like everyone reduced their cost. But if you forget about A, let's say you forget about A, you only go from here to point B and point C, you will find it's exactly the same cost. So there's no point of like forming this Uber pool with 3 people. Just maybe B and C is the same cost, and it increases your time to get to your home. And here, so Shapley Value is a concept to help solve this problem. And so the formula looks a bit complicated, but actually the basic idea is, can I kind of like consider all the situations in the right and take an average of them? So what does that mean? Like, let's take the passenger A, for example. So suppose like B and C already decide to form a collision. So it's from a cooperative game theory. So suppose B and C decide to form a collision, and then now A joins. So what is the marginal cost gets increased? And the weight before is more or less like the probability of this situation shows up. And same idea you apply, like for example, only B is there. B needs to go home, and now A joins. So what is the marginal cost? And you take all this situation into consideration, and then you average them out. Now you have they call it the most fair solution for cost splitting. And I know that some Uber folks here, maybe we can ask them afterwards, do you really split our costs like this? Now, how does that map to a machine learning model? Because in a machine learning model, you need those features work together to form a strong signal, and that gives you predictive powers. And how do you allocate those prediction score to each feature? Actually, it is a similar concept here as the cost splitting. And that's why this like theoretical framework gets introduced, and it kind of beautifully solves this problem. If you replace the phi you see before in the feature attribution to the Shapley value. And then you kind of like this, and this Shapley value have pretty good properties. And this table actually from the paper called Consistent Feature Attribution for Tree Ensembles. It satisfies local accuracy. What does that mean? Like, if you compute Shapley value directly, it sums up to your predictions. So you can kind of like decompose your final prediction into how much each feature contributes. And it also satisfies a property called misness. Means if the feature does not exist, it's not there, it should assign no importance. It should give you a 0 Shapley value. And the last one is the consistency. It's a bit tricky to interpret. So the basic idea is like if the true model changes and assign higher weight to one of the features, this Shapley value should not decrease. So it's some sort of like theoretical guarantee. And if you look into the original algorithm, you might notice it actually takes exponential. The complexity is exponential because you need to take all this computation, all this permutation into account. So luckily, if you play with tree models, your life is much better because in tree model, there's some simpler way to compute it. Basically, you just need to track down all the branch in the tree. And what's better is SGB Boost and LightGBM have a built-in support for this algorithm. And so very fast and help you to compute this Shapley value. So this is the story for a tree model, right? Now, what does that mean for neural network? So there's an algorithm developed inside Google by Mukund, Ankur, and Chichi. So there are research scientists in Google, and they wrote this paper, I believe, is 2016. So it is the algorithm called path integrated gradient. You can use it to analyzing image data, text data. The right-hand side actually is a sequence-to-sequence model. So you can actually use it to analyzing very complicated machine learning model. And what is less known is this algorithm also have a very good theoretical guarantee. So it's a variant of Shapley value called Shapley. So that extend the finite game to an infinite game. And the computation is pretty simple. So if we look at this slide, the basic computation is just compute the partial derivative to the input, and then do the line integral. So let's forget about all this, like all the formulas above. Let's look into the graph, all this blue, green, and red line. All right. This green line represents the path integrate gradient. So what it does is it assumes you have some starting point. For example, for image, the starting point might be the mean statistic of all images, or it could be all black or all white images. So it represents a state of no information. Like for NLP, it could be the same length of like sentence with null token. So it represents a state of no information. Now, you go from the no information to your current feature space. So that represents go from S1, S2 to R1, R2. And you compute the line integral along this line. So that gives you the path integrate gradient. So it also satisfies all those beautiful properties. In the original paper, it called local completeness, which is the local accuracy. Means if you sum them up, all the feature attribution should equal to your prediction, minus the baseline's prediction for sure, because you start from a no information state. It also satisfies the missingness that's called sensitivity. That means if the feature is same as the baseline, if you don't walk in the path, the feature actually will assign 0 value in the attribution. And also it satisfies the linearity property, which if you have two networks, you sum them up together, you ensemble maybe 100 model. And when you map back to this feature space, it satisfies this like linearity. So also very beautiful theory. Here I just want to point out another is actually is the blue line. Blue line is also a common way to get interpretability. What that do is it try to mask, so only mask one of the features and compute the prediction for the rest, and then do it iteratively. So if you have m features, you do n function evaluations. So that's called ablation. So some people might argue like, why is a linear path? You can go through any other path, right? This red line, you can do any path. And certainly, like this like linear path was pretty fine, and it guarantees some property. So to use this algorithm, there's certainly some additional assumptions. The first one is like all the operator in the graph should be differentiable. So if you have some kind of embedding lookup, probably you need to start from the embedding space. So it doesn't work with non-differentiable operations. And also you need to specify a baseline which represents the no information state. So you need to know like where to start in order to compute this path integrated gradient. And this is the theory for the neural networks. And this like green dot just represents some numerical approximation scheme. You might do some numerical integration to compute the line integral. All right. Now, we have all this theory we need. Can we apply this algorithm to a real-world data set? So here I picked one of the Kaggle competition which is the text normalization competition. So in this competition, you are asked to convert a written form English into a spoken form. Let's pick maybe the date here, 2006. In the number, it's just 2006, but how do you know it should be pronounced as 2006, right? You probably need to first predict which class this token belongs to, and then based on the token class, and then you run the corresponding translator. And in this data set, there are in total 9.9 million tokens, 748K sentences. Each sentence contains at least one token that needs to be translated. Because a large portion of these tokens actually remains its original form. If you check the plan means like the written form is the same as the spoken form. The other is the punctuation. And you can see it contains the 93.1% of the data. So most of them, actually, you don't need to do any transformation. You still get high accuracy. And I would say here, accuracy might not be the best metric, but that's what the competition uses. And you can also see, like, even within all the rest of the minority class, it's still a highly imbalanced problem. For adjust, actually, you can't even find it looks like there's zero adjust, actually, but there's some of them. So here is how the problem is set up. Now, how can we develop a machine learning solution to solve this problem? I would like to first give credit to the team I take the buff. I don't know how to translate from Chinese to English, but that's how it goes. And also several most voted kernels. And that's why I like the Kaggle community, because people are willing to share the solutions, and I learn a lot from them. So here, it first formulate it as a multi-class classification problem. So for each token, let's first predict which class it belongs to. All right. Once we know the class, we can do a rule-based translator, which probably is pretty easy to construct. So here, the first step I did is called the context window generation. So what that does is you can only use that single token. It's fine. You can use only that single token to develop a classifier. But it would be better if you can incorporate a context window, like that means the token before and after. So that adds more context to your prediction. And here, I just use like one context window means there's a center token, which is the token 2. And then I incorporate token 1 and token 3 in the solution. And you might see there's some negative 999, which is just a boundary value. What that does is just indicate it's the beginning of a sentence or the end of the sentence. So, sure, OK. Now we have this like context window generation. The next step is to transform it into a dense matrix, because originally it's just a character. So how do you convert it to a dense matrix? The first step, you pad this like token into a fixed length. And the reason I want to pad it is tree models actually cannot handle like arbitrary length sentence. And I want to use both tree and neural network to analyzing this data. So first, either truncate or pad it. Here, I choose a length of 20. If it's too long, it just gets truncated. If too short, just pad it. And then you do a Unicode encoding, which here Unicode encoding brings a lot of advantage because it actually captures some implicit grouping. So if you check the Unicode, you might find alphabet is in the same range, numbers in the same range, and then some like special symbol there in the same range. So that could help the tree to find a good split point. Unicode encoding, fine. The next step, actually, you don't need to do that for trees. But since I also use the neural network to solve this problem, I do an order preserving rehash. So the reason is the largest Unicode number goes to more than 60,000. But actually, the unique character is only 3,000. So if you want to encode based on those integer values, it's probably too large to embed. So I do an order preserving rehash, means I will first sort all this unique character, and then I re-index them. And finally, you do it for token 1, 2, and 3, and then you concatenate them. And in the middle, I insert some kind of a boundary value just to indicate the first is the token 1, the center one is token 2, and the last one is token 3. So now you transform the data into dense matrix. And then you can run a machine learning model on it. So there's two models I use in solving this problem. One of them is just a simple multi-class attribute boost that does one versus all scheme. And the second one is the neural network I use to analyze in the data. So here I pick a one-dimensional CMM, which just trains faster so that I don't need to spend several days to train a LSTM. And it uses the kernel size is 7. So you have this convolution to capture this local correlation. All right. And then the second layer is a mass pooling. So unlike the original paper for 1D CNN, I do a character level pooling. And the reason is the most important is actually the token 2, the center token. You actually want to preserve some position information. So I do a mass pooling actually along the character level. And then finally followed by some fully connected layer and the soft mask. Now we have all these two models to solve the same problem. So the training is also pretty straightforward, split 9 million used as a training and validation sample. For 1D CMM, actually I do a little bit more to do the oversampling. So because tree model itself is pretty good because when you do one versus all, even you are dealing with minority class, it might still be able to capture some signal. But for neural network, it's probably not the case. You need maybe cost-sensitive learning, or you might want to do some oversampling. So here I just pick oversampling to address the class imbalance problem. And then finally, the testing data is just the remaining 0.9 million. The hyperparameter was picked just by experience, not too much theory underneath, but it worked. Now, let's try the final result of these two models. Here I just showed the test data label distribution, still remove the majority class. And you can see for attribute boost and the neural network, probably the final accuracy is pretty close. But actually, if you look carefully, even I do an oversampling, it's still the 1D CNN failed to capture the minority class. So here it's not to compare attribute boost or neural network or trying to develop a neural network model to beat the attribute boost. But I want you to understand this model characteristic so that later on we move to the model explanation. All right, so once you all have all this model, all this data pre-processed, here we comes to the local explanation. So I pick some of the data just to give you a sense on how this explanation look like. First, the one above is the attribute boost, the tree shop, just comes straight out of the attribute boost package. And the figure below is the path integrated gradient for the neural network. And I pick a sentence like, this token is more than 3,000 pounds was available in the building fund. So that is the 3,000 pounds is the token we try to predict, all right? So the true label is money. Now, in this figure, we can see both models actually predict correctly. So both of them predict it is the money. And both of them actually capture this symbol, this pound symbol, and use it as a prediction. There's a little bit weird part of the convolutional neural network. If you take a look on the 3,0,0 token, so you might see why the comma is a negative in the neural network, while it's a positive in the SGB boost, right? So it seems to me the SGB boost can actually capture this interaction between the pound and the comma. While since you are using a convolutional neural network, so what it does is a sliding window and then capture some local correlation, right? It moves the window, capture local correlation. When it goes to the pound side, it captures strong signal in the pound. So that's why you see a very high value in the pound. And then once you go to the 3,000, it actually might capture it as a number because it's a convolutional neural network. So that's my explanation on why you have a different sign in the comma sign. And let's also see some example on maybe when does SGB boost predicts wrong while neural network predicts right? So here's one of the example. The true label is planned, so you would pronounce as it is. It's the Paxos. And in this sentence, SGB boost actually thought, I think it's this letter, while the neural network thinks it is a plan class. If it's a letter, you would pronounce as PASOK, so you would pronounce them separately. And the figure above is I try to apply this Shapley Value analysis on the plan class. So I try to understand why this SGB boost thought it is a plan. Why I want to see why it does not capture it as plan. And it seems to me is it give negative value to all those capital letter afterwards. So that's how I feel what SGB boost does here is it learns a rule, some kind of maybe a linguistic rules. It forces maybe if you have multiple capital letter, it should not be a plan. So that's some kind of my interpretation. And while for this convolutional neural network, it just capture the whole window. And interestingly, there's actually a reverse example. While it should be a letter, but the SGB boost was able to capture it, while CNN would predict it wrong. And if we take a look into it, what does SGB boost does is it also capture if you check there's 2-0, denotes actually there's no token at all at that time. And it seems to me what SGB boost does, it captures a shorter token as it's more likely to be a letter. While the convolutional neural network actually have some similar attribution pattern as the one we see before. So as you can see, there's some analysis you can use this tool to generate local explanation, some kind of a way to look inside your model and understanding why give such prediction for certain features. It does not guarantee you give you a very explanation that match with your prior. So there's no such guarantee. But it guarantees to give you some local explanation that you can use it understand why this model gives me prediction at a certain point, right? If you really have a strong prior, for example, if you are from linguistic background, you know this rule must be wrong. So what you can do is, so one, you can pre-filter that using pre-processing. You can just assign the class to that token. Or you can construct some kind of as per rule and use it as a feature in your either SGB boost or neural network. So if you have a very strong prior. So in here, I would say, although they have a very beautiful theory behind the feature attribution, it does not necessarily match with your prior. So it means that it doesn't necessarily match with your domain knowledge, all right? And now we are going to the advertisement type. Oh, sorry, it's the deployment type. So I would like to show you how you actually deploy your models to a production system. And here I want to talk about one of the products in the Google Cloud is the Cloud Machine Learning Engine. It actually helps you to deploy your model and then getting prediction from it. So now it's a demo time. All right. So let's first move is just a normal GCP platform. And what we want to find is from your left panel, you go to the AI platform, and you go to the models. So here is the place that after you train your model, you have all these like Attribute Boost model train, you have all your TensorFlow model train. Now here is the place that helps you to deploy your model. So let's first deploy this Attribute Boost. So since I have them trained already, to save us some time. And here, the model is Attribute Boost. It allows you to create multiple versions. So if you want to like switch between different versions. And you might say, it's the first version of it. It's Attribute Boost. Since Attribute Boost serialize all the model way, you can just pick any Python version. You can pick there's like scikit-learn, TensorFlow, and Attribute Boost. So let's pick Attribute Boost. There's a different version it's available. Just pick the latest one. So because I trained from the latest one. And now you can pick machine type like single core or quad core. I don't pay for it, so I would pick a quad core. And so be careful if you are really pay for this system. Make sure you pick the, based on your latency requirement, your compute requirement, pick the right machine type. There's a Kaggle Day folder I use. So what inside this folder is just a file called model.bst, which is the model export from the Attribute Boost. You pick this folder, then you can select like auto scaling or manual scaling. Means auto scaling, it would have like scale to 0 if there's no request comes in, or you can set some minimum number of nodes. So that here it really depends on your like latency requirement on how fast you want to get this result back. Pay attention to this the number, and that's it. You successfully deploy an Attribute Boost. And let's move to the TensorFlow, mostly similar workflow. Let's say V1, 217. Let's pick TensorFlow, latest one. Pick the runtime, and yes, core for sure. And what you need to do to deploy a TensorFlow model is you actually need to export it in a safe model.pb. It is a bit, yeah, sorry, this time's up, so I would go faster. Just deploy it. And that's it, you have to deploy all the model. So once it is deployed, how are you going to use it? So here I use a notebook. Actually, it is a notebook solution, also just get released. I really love it, easy to use, and cannot work without it. So what it does is, let's maybe just do one of them. So first, I load the feature in. Pick any of the data. And the sample looks like just is an encoded feature vector. So what you would do is you specify the project name, which is the one I just specified. The model name is SGB, as you see. The version is V1. So that's the URL you are going to send request to. And certainly, you need some credential. Not everyone can access your model. And then you just send a request to this endpoint, decode it, and you are going to get back your prediction. And since we are talking about explainability here, we are going to have an alpha release for the explainability features. So along with this prediction, we will also return you with the attribution. So that supports both TensorFlow attribute boost. That feature is invite only. So if you're interested in using the explainability features, come and talk to me afterwards so I can write down your emails and all the information. Or you can feel free to contact me through Kaggle email, LinkedIn, or the Twitter I opened 2 days ago. Now, just a brief conclusion. This method actually have a very good theoretical background, the Shapley value. You can use it to compute feature attribution. But it's mostly local analysis for now. You can see just based on some, for this specific feature, you get this feature attribution. If you happen to deal with tabular data, you can actually use, you can do actually some kind of aggregate analysis. You compute this Shapley value for each of them. Then you can compute the distribution of the attribution. And you might be able to use it to detect like skewness, train test feature distribution drift. The last thing is there's more features to come in the alpha release. So if you are interested, just let me know. Right? That's all for my talk. And we still have 30 seconds for questions.
Yeah, could we get some claps for Ran? Thank you so much, Ran. That was great.